let's go through and do an example using this equation so we can understand how it works. Let's say we have two large parallel plates. Between these two large parallel plates, we will have an electric field that's going to be a constant electric field. Considering the electric field has this direction, the top plate, Hillary, is a positive or negative charge? This has a positive charge. We know this, Hillary, because?
Because electric fields go from positive to negative.
Electric fields go from positive to negative. True. Why do electric fields go from positive to negative, Bailey?
Because it's defined by a small positive test charge.
Because it's defined by a small positive test charge. Great. So we know that the electric potential difference between these two plates is 12 volts. Let's say that D, the distance between the two of them, is equal to 1.0 centimeters. And let's define this plate as plate A and this plate as plate B. So what we're going to do is we're going to actually derive the equation for the electric potential difference that exists between these two plates. So electric potential difference, VB minus VA, the potential at B minus the potential at A, is equal to the negative of the integral from A to B of the electric field dot product with ds. So as we go from A to B, so we go from here, we're going to go directly from A to B. Therefore, this is going to be equal to negative of A, B, E cosine theta ds, because it's the dot product. What then is theta, the angle between? Tim?
1/8.
No, I'm just starting with a general statement. What's the angle between?
Oh, E and ds.
E and ds. So class, point in the direction of the electric field. Point in the direction of ds. You should maintain pointing in the same direction. Because we're going from A to B. That's what B minus A means, final minus initial. So we're going from A to B. So the direction of ds is the same as the direction of the electric field. So this is equal to the negative of the integral from A to B, E times a cosine of 0 degrees, ds. Okay, cosine of 0 is just 1. We know the electric field is constant from A to B. We've already shown that. We're going to have a constant electric field here. So we can take the electric field out from underneath the integral. In other words, the change in electric potential or electric potential difference is equal to the negative of the electric field with the integral from A to B of ds. What is the integral from A to B with respect to S? What is that in this particular example? Vasily?
Just D.
Just D. So the electric potential difference is equal to negative ED. This is for a constant electric field. You should have this memorized. Memorize. I'll take the D off. And you should be able to derive this. We deal with enough constant electric fields that it is useful to have memorized, and you can simply use it if you are not asked to derive it, but you might also be required to derive it. So, what does, yes, gentlemen, what's up? S is just like going from one location to another. The reason we use S, you could use X or R or Y or something like that. The reason we use S is because we're not always going to be going in a straight line. So it could go in a curve. Not yet, but don't worry. So what does the negative mean? To draw the parallel, we have the Earth. We have the gravitational field. If I take a mass and I put it right there, what happens, class, when I let go of the mass? goes down. Okay, what happens to the gravitational potential energy? It decreases, right? So if I take a mass, it's going to go in the direction of the gravitational field, and the gravitational potential energy will decrease. Same is true if I take a positive charge and place it right here. If I let go of it, it's going to go in the direction of the electric field, and therefore it's going to decrease in electric potential energy, and therefore decrease in terms of the electric potential difference, which is what the negative means. It means the electric field line is always in the direction of a decreasing electric potential. Now, what's especially interesting about this is that's what happens if I take a positive charge and I let go of it in this electric field, which is down, right? So the positive charge is going to go down. What happens instead if I take a negative charge in this electric field, which is down, and I let go of it, class? It's going to accelerate upward. So what's going to happen to its electric potential difference? It's going to increase. Okay? So notice, it's much more complicated to think about what happens to a charge in terms of its electric potential energy and electric potential difference, because you have a positive and a negative charge that you have to think about. All right. What happens? We're going to extend this question. Example part B. Let's say we release a proton at plate A. What is the velocity of the proton at plate B? So now what we're doing is we're taking a proton, putting it right here. We're going to let go of it. It's going to accelerate and run into plate B, and the question is, what is the speed of the electron when it gets there? How would you like to start, Gary?
We can use. Wait, what did we give it?
We know the electric potential difference and the distance.
Can we find E?
We could figure out the electric field, but at this point, we could figure out the electric field. So we could figure out the electric field. We could then figure out the electric force. We could then figure out the acceleration. We could then use UAM. Not going to do it that way. Yes, we could certainly do it that way, but that's not the way that, I think this way is a little bit easier. There were several steps listed there. What's another approach?
Conservation of energy.
Conservation of energy. Why, Tyler, is energy conserved in this particular case?
Because it's a conservative force.
Sounds good, though. That sounded really good.
Great.
Yeah.
You like the confidence in that, though?
It was good. John? Why is mechanical energy conserved? Travis?
No friction, no force applied.
Remember, no friction, no force applied. Therefore, mechanical energy is going to be conserved. So we start out with mechanical energy initial equals mechanical energy final. We'll set our initial point at A and our final point at B. What sort of energy does the object start with? Eugen? Electrical potential energy. Okay. So U sub E stands for what, Michael? No, doesn't stand for electric potential energy. Jenkins?
Elastic.
Elastic potential energy. Okay, well, we'll do EL then. Oh, wait. Elastic potential energy. ELE is usually what I use. I know it seems like way too much, but alas, it is the case. The electric potential energy initial. Class, does it start out with kinetic energy? Does it start out with elastic potential energy? Is it on a spring? Does it start out with gravitational potential energy? I like, that was a lot of different answers to that one. Sierra, talk to me.
Oh, right.
Remember, it's an atomic particle, therefore the gravitational potential energy is negligible relative to the electric potential energy. So while it may start with gravitational potential energy, the gravitational potential energy for atomic particles is negligible. Mechanical energy, final. Flat.
It's going to have a velocity, so kinetic energy. And it's still going to have electric potential.
Now, the interesting thing about this is we don't actually know if it starts or ends with electric potential energy, because we don't know what the electric potential energy is at either place. All we know is the change in electrical potential, or the electric potential difference, or the change in electric potential. So what we can do here is we can rearrange this. So we'll say negative kinetic energy final is equal to the electric potential energy final minus the electric potential energy initial. Well, this is the change in electric potential energy. Because it's the change in electric potential energy that we can actually figure out here. What is the change in electric potential energy going to be equal to? Look.
Potential difference times Q.
Remember, the electric potential difference is defined as the change in electric potential energy divided by Q. Therefore, the change in electric potential energy is equal to Q times the electric potential difference. So we have negative 1/2 mv squared, or v final squared, excuse me, is equal to Q, the charge, multiplied by the electric potential difference. Okay, we're solving for velocity final. So velocity final is equal to 2Q electric potential difference divided by mass, the square root of velocity final. Please give me all of these numbers. Meg. Q
is 1.6 times 10 to the negative.
Multiplied by electric potential difference.
Not sure. Do we not know that? Oh, okay. Oh, 12. Sorry. And then mass is
Proton.
1 something times 10 to the negative 30 something.
Oh, I missed this negative. I'm sorry. There's a negative there. So we have a negative square root of 1 point what?
Trying to find my table of information.
Table of information. Also probably in your brain at some point. But it will leave and come back at various times. Zach?
1.67
Times 10 to the negative 27. Yeah. I'm not allowed. He's just said I'm not allowed. We have done something, or we put something in incorrectly. You're right. We can't take the square root of a negative number. Jenkins.
Delta V should be
Why?
because you're losing.
Remember, the electric field is always with a decreasing electric potential, right? So we're going from a higher to a lower electric potential. So the change in electric potential is going to be, or the electric potential difference is going to be negative 12 volts for this proton. Now, we don't actually know if this one's 12 and this one's 0, if this one's 24 and this one's 12 or whatever. But we know that the difference between the two is negative 12. So we have a negative here. Therefore, the velocity final of this proton. Please. Tyler, what'd you get?
I didn't.
That's sad.
Um,
We have two negatives, and negative times a negative, which is a positive.
4.79 times 10 to the 5th.
I need more than just
4.7952.
That's in meters per second. Let's convert to miles per hour just
Times
for
10
fun.
okay, never mind.
Okay, times miles per hour. Let's go, so 3,600 seconds in 1 hour, and we have 1,609 meters in 1 mile. Meters cancel out, seconds cancel out. We now have the velocity final, or the speed final, of this proton.
107,288.
107,288. With sig figs, we'll go with 107,000 miles per hour. 107,000 miles per hour. Class is 12 volts. A lot of electric potential difference. No. Is 1 centimeter very far? No. And yet, we can get a very large velocity for this proton because the proton is has a very small mass, and that electric force is going to cause it to move quite quickly.